In this lecture, we look at the properties of the Ols estimator in a time series model, which is a static model, and we do that under the Gauss-Markov assumptions. We have the following setup. So I have a linear regression model and all the Gauss-Markov assumptions are satisfied. Dependent variable yt, explanatory variables x2 through xk, and an error term epsilon t. So under the Gauss-Markov assumptions, that means that every time series is stationary, the x variables are exogenous, the error terms are homoscedastic, and the error terms are not autocorrelated. So to illustrate the properties of Ols and also to illustrate the Gauss-Markov assumption, let's consider a Monte Carlo simulation. So here I have time series data starting at January 1st going to May 19. I have two explanatory variables, x2 and x3, shown in this graph, and from the graph we can clearly see that this is not a random sample. There is correlation between observations over time, and we can clearly see that because of the cycles in the data. However, I have created a simulation such that both x2 and x3 are actually indeed stationary. They both have an expected value of 0 at each point in time. So let's see how we can simulate the error term and still fulfill the Gauss-Markov assumptions. So I'll do EPS here. So we need the first error term. I can simulate it from any distribution, but let's do the normal one. Like this. First of all, the expected value. And now it's really important that I put a 0 here, and I cannot make this expected value depend on any of the x2 and the x3 values. That would make the x variables endogenous. Next, let's put a standard deviation, and the same thing goes here. I cannot make this standard deviation be dependent on any of the x variables because that would make the error terms heteroscedastic. So let's just do something, maybe 0.2, like this, press enter. If I now copy this down like this, then remember that when you do two random drawings in Excel like this, it will do it in such a way that this will be independent of that, which will be independent of that, and so on. That means that my error terms will not be autocorrelated. There is no correlation between, let's say, this term and this term. They are uncorrelated, so I have no autocorrelation, satisfying also the fourth condition in the Gauss-Markov assumptions. So again, correlation between these two x variables or correlation between these two for the x3, no problem. Correlation between these two in the error term, well, slight problem. At least we violate the Gauss-Markov assumption in that case. And we will look at this particular issue in a later lecture. So we can now simulate the y variable according to our model. So y is just equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus the error term, just like this. That's my y value. Copy this down like this. So finally, I also need to know that my y variable will be stationary, but I know that it will be because x2 is stationary, x3 is stationary, the error terms will be stationary as well, constant expected value, constant variance, and in this case no autocorrelation. And since the y variable is just a linear combination of these x2, x3, and epsilon, we know from before that this must be stationary as well. So here is a simulation satisfying all the assumptions, all the Gauss-Markov assumptions for a time series linear regression model, which is static. Yes, we can see it's static also because the observation on the y variable depends only on the x values at the same time period. If this one had also if this one was depending on this one, then it would be dynamic. So let's see the consequences of doing OLS on this model. So let's just use linnest and let's do the statistics as well. So we do 5 rows. Like this, the y variable, 2 x variables, intercept, and statistics, shift control, enter. And remember, these are the parameter estimates. The second row, those are the standard errors. B1, 0.01 is the estimate of beta 1, which is 0. B2, 0.997 something is the estimate of beta 2, which is 1. And B3 minus 1.01 is the estimate of beta 3, which is minus 1. Alright, so here are the results of the OLS estimator. First of all, it is unbiased under the Gauss-Markov assumptions. Let's check this. So let's focus on B2, for example. The beta 2 is 1. So if I F9 this experiment, this B2 should on average be equal to 1. And it does seem to work. It's about equally often below and above 1. The OLS estimator is consistent. Again, we need just some additional weak assumptions that are typically satisfied in empirical studies. I'm not going to illustrate that because then we would need to increase the sample size and make it bigger and bigger and bigger. But had I done that, you would see that B2 would get closer and closer to 1 in each simulation. We can also show that OLS is blue. It's the best linear unbiased estimator in this case. Linear, remember, it means that the OLS estimates are they are all linear functions of the y data, and best means that it has the lowest variance among all linear and unbiased estimators. Also, the OLS standard errors are consistent. So these numbers here, which are so important for any kind of inference, I can trust those. Those will be consistent. And finally, that means that I can do inference. So as long as the error terms follow a normal distribution, then all inference will be exact. And if the error terms do not follow a normal distribution, the inference will be approximately correct. And the larger the sample size, the better will be the inference. So to summarize and compare with the cross-sectional data, we have exactly the same results. The only difference moving from cross-sectional data to time series data is that we need some additional assumptions, and we also need to drop this assumption of a random sample. The most important alteration in the assumptions are the fact that when we condition on our x variables, we need to condition on all of the observations, not just the x data for that particular sample point. That goes for the expected value as well as the variance. And the second really important point is that we need to add the assumption of no autocorrelation to the collection of Gauss-Markov assumptions. That assumption was trivially satisfied when we work with cross-sectionally data, as long as we were able to make the assumption of the sample being a random sample.